discussing a PhD thesis defense by Anthony Simeonov. He's at MIT. The video is in the show notes, and all the papers and details are in the show notes. I want to keep this high level because we're not a technical podcast here, so we're not really trying to explain the difference between neural radiant fields and what it means for point clouds and whether RGB pictures are more difficult or less difficult to capture for robots than point clouds, and why RGB is more important than point clouds and things like that. But that's really for technical people. Our audience here is, as far as we know, sort of a broader audience of investment professionals and also people who are interested in AI, because we talk a lot about AI, and maybe some people also who just want to know what's going on in Silicon Valley in general. We're based here in Silicon Valley, and the purpose of this podcast is to give people a sense of what it feels like to run a hedge fund. So it's not to talk about AI or by any means discuss papers or something like that. We're not an academic paper discussion forum, but we do talk a lot about academic papers because that's our approach here at Orange Capital Partners, right? We are trying to actually, it's our job to find the Venn diagram crossings between science, technology, and entrepreneurship. So we have to, by definition, understand all those three bubbles, and then hopefully find the intersections between those three bubbles. So that's the goal. That's how we work. That's not how every hedge fund works. And as you know, we always say, do your own work, and just please don't use this platform as a contact. This is not meant to solicit any kind of investment or anything like that. This is hopefully educational, and if not, then maybe entertaining. What we're trying to do is really get across the fundamental message, which is that reading is yoga for the mind. Reading any kind of thing, whether it's novels, whether it's academic papers, or X tweets or anything like that. I don't know. Is that a word, X tweets or X's, or what is the word? I think Musk has to clarify this once and for all. So what we're trying to do here is why do we talk a lot about academic papers? Well, because that's one of the main sources of knowledge and inspiration for us, and for better or for worse. It's not the most fun thing to do sometimes. Sometimes it's fun, sometimes it's cool. We spend some time also at Stanford attending seminars. So academic papers are a good source of inspiration for they might have a bad rap sometimes, but in AI, in particular in robotics, I don't think so, because it's moving so fast and the language is really accessible, at least sort of in the sections that are meant to be accessible, like introduction and conclusion and things like that. So you can really learn quite a bit without being in the weeds, without having to understand the nuances between the kind of dot product multiplications that are used in this formula versus that formula. And I think that's really powerful. That shows you how the field is growing. And I think the reason we picked this PhD thesis, by the way, it's the title. It's Geometric Learning for Robot Manipulation. So what is this PhD thesis really trying to do, right? I mean, let's try to keep it big picture here. So if we look at the problem setting, Anthony is setting out to solve, right? Imagine you have a robot and it has to pick up a mug and put it somewhere. Or imagine an Optimus robot in a factory that picks up a wrench and puts it somewhere, or takes a screwdriver and has to screw a screw, but the screw is not upside down, it's the other way around, because the screwing is happening, let's say, at the ceiling, right? So what we're dealing here is with different geometric relationships between the grasp, the thing that is being grasped, and if you want to also have multimodal, that means you are grasping something and then putting it into something else, or screwing a screw into something else. So the problem is how do you keep the geometries in line so the robot knows that if the screw is upside down, it's still a screw, and it still has the same physics, meaning the top is where you hold it or put the screwdriver in or whatever you're screwing it with, and then the bottom is where you screw it, right? You want to understand these relationships. And I think this PhD thesis by Anthony is a good example of the evolution also of AI, because he spent obviously a couple of years doing this PhD. His undergrads from UC San Diego, I believe, San Diego or master's, and then PhD at MIT. So it took him a couple of years to do this. And what he shows, I think, is really how the field is going sort of from an engineering deterministic discipline into a more iterative AI discipline, for better or for worse. So what does that mean? So he starts with, there's three big ideas that he's selling in his PhD. One is a sort of what he calls, SE3 equivariance, neural relationship type of approach. What does that really mean is he's trying to capture geometries through learning. So he's using learning, but he's learning geometric relationships between objects. So think about it this way: like you wanna you're using computer vision or LiDAR or something like that, so sensor fusion. But what you're trying to do is you're trying to sort of fix the relationship between the object of interest, so the robot, so the robot's arm or the finger, and the mug, and the sort of the edges of the mug that the mug is being held at. So there's a certain sort of rigidity, in my opinion, to the whole approach. And then in the next phase, he's using what he calls diffusion models for pose estimation. So now he's becoming more iterative in the sense that he's not trying to learn, he's not trying to see what's out there and then sort of rigidly decide, okay, I'm here and the object is there and it needs to go to point Z, and all these relationships are, what equivariance means is that I have a fixed relationship in my relationship with the object, no matter how I turn it and how I twist it. In the diffusion model part of the PhD, he's trying to sort of predict the pose of an object relative to the robot based on diffusion models, which is what are diffusion models? They're sort of a computer vision tool that helps us define something, based on this idea of diffusion, which is an idea from physics. And again, I don't want to go into the technicalities. But what the upside is in this type of approach is it's more iterative and it's more flexible. And then lastly, the last thing he does is actually learning in sim. And I think that's where it really gets exciting for us, because that really shows you where the field is going. It's going towards at scale parallel learning of skills in simulation. He's showing how they digitally create a digital twin of a kitchen. You can supplant kitchen with factory or lab or any kind of cluttered environment. You have a digital twin, so you can literally create a virtual kitchen with microwaves and doors and cabinets. Or if you're Tesla and you're training Optimus, you can do that in the factory, and then have the robot literally and now here's the upside, right? What they were trying to do in the first two approaches, so in the equivariance approach and in the diffusion approaches, what they're trying to do there is really minimize or optimize the kind of learning that has to be done, the imitation learning or the instructions, right? You have only so many people that you can have show the robot what to do, right? So the robot has to quickly understand what's going on. In the simulation part of the PhD, in my opinion, at least that's the way I see it, and this is obviously preaching to the choir because we've been talking about this for over a year now, how we think the future of robotics is in simulation, and that actually the work towards real-world robotics goes through the virtual world of simulation. What we like to do here is actually go back and say, no, we can teach the robot actually really all kinds of different poses of of a thing and have it deal with the different poses and the different geometries without any priors. So we don't need this equivariance thing. Well, we can maybe include some of it, but the point is we can have simulation, whether it's Isaac Sim with Jim, Jim, the NVIDIA platform or some other platform, where we can actually in parallel train a robot at scale in sim and then have the sim to real translation. Now there's some technical aspects to this. For example, they start with behavioral cloning and then use reinforcement learning, so that in other words, the question of any kind of in-sim training is always how far do I sort of initialize the learning object, in this case the robot, and that can be done through behavioral cloning. So I show the robot a couple of instances of how I screw a screwdriver, or how I hang up a mug on a hook, or put a mug in the cabinet and things like that. And then I have in sim at parallel, at scale learning, until it gets good enough, until it has the kinds of policies that I think are worth translating into from sim to real, and so on and so forth. So lastly, now I want to also introduce a different idea that is not part of the PhD, but that I just picked up recently at Stanford, and that is sort of the toolfinder paper that came out recently. I think we spoke about this in the context of NeurIPS 23. The idea is that imagine you have, okay, let me step back for a second. So what's going on right now in the large language model community is this idea to use large language models as operating systems. Now, in order to have large language models as operating systems, you need to have a way for them to understand what is the next thing they should be doing, and what is the next skill or the next API they should be calling to solve a problem. So in other words, the LLM becomes not just sort of a fixed learned model that does everything. The LLM becomes a semantic understanding platform that understands which problems to solve, and then iteratively uses certain tools. For example, a simple thing, the LLM is asked to solve a problem. It has a math problem. It then acquires, calls an API for a math problem, or calls an API for a Python program, does the program and solves the problem. So this goes into the realm of reasoning. This goes into the realm of O1 or DeepSeek R1 models. So this is a big topic right now these days. But what I want to talk about here is really the idea that we could have robots in a factory doing the same thing. Basically, self-evaluate tools and then call them. So have a robot equipped with some sort of large language model that calls upon itself a tool. Let's say in this case, I don't know, screwing a screwdriver is a tool, is an API that it calls from a set of tools, and it doesn't have to learn that per se. So we could have basically sort of a convergence of two big movements in robotics that have been going on for a while. One is sort of the generalized learning. So you have a model that basically is a general, our sort of AGI type model, like a large language model for a robot. So the robot knows how to screw stuff, put stuff somewhere, clean stuff. Or you could have the different approach where you have skill-based learning. So you have really very good sort of APIs that the robot can call. And what that means is then, of course, you have to have, and that goes in the direction of toolfinder or the React paper, two papers also attached in the show notes that I recently discussed in one of the Stanford classes. The React paper is, in both cases, the skill there, of course, or the training objective is for the robot to understand what skill is necessary and then call the appropriate API. So that's the sort of the idea, and I think in the big picture, what this means is that you have a robot factory full of robots that self-evaluate their tasks and call upon the skills necessary to solve the problem. And therefore, you can sort of modularize the learning process. So you can have specific skills trained for the particular robots, and have the robots themselves equipped with a model that is particularly good at identifying the skills necessary and then calling on APIs. Of course, you have to solve the embodiment problem. That's not something I want to discuss here, but I think as a big picture idea, to me, that is worth exploring. So to summarize, Anthony Simeonov's PhD defense, I think really interesting from different perspectives. I think one is the actual work itself. I think it's always interesting to see what people are doing, but more important, I think it's a really nice example of how the field has evolved from a more engineering, deterministic, rigid, mathematically defined way of defining geometries and relationships between robots and the environment towards a more iterative approach, finally culminating in a simulated, parallelized approach towards learning, which I think is the future. He, for example, thanked David Fox from NVIDIA and UW, which I think he's one of the proponents of this, of course, with being part of the NVIDIA robotics team. But we believe that that is the future, and I think that's really important also. And then what we also spoke about is this self-evaluation process, embodied in papers like React and toolfinder, where we could have the same approach towards robotics, where robots are trained to identify problems and then call the appropriate APIs to solve the problems. I think lastly, what I want to say is now tie this all together to the purpose of this podcast. I think this is a nice example of how the hedge fund industry, in our opinion, works. Right? We have a pretty good understanding now where the science is going. We have a pretty good understanding what's possible, and then we also see what's going on in the real world. For example, Tesla is investing in Optimus. We have Figure. We have others investing in humanoid robots. And the reason we're so bullish on this is not just because Elon Musk's saying that it's a great thing. Of course, that's part of it, or the Figure CEO or whoever is touting this. I think what's important is also we're actually seeing there is a line of sight in the scientific community that this problem can be solved at scale with real examples and with real practical applications. And there's a path, because the eventual solution, in our opinion, it always has to be something more flexible, iterative, learnable. It can't be rigid, and that is exactly what this combination of Anthony Simeonov's PhD and also the inspiration we got from the Stanford classes about self-evaluating AI that we got from there. So in that context, I think this is a really important. We can't emphasize enough how important this is, and hopefully we can go back maybe in a year or two and use this particular episode as a checkpoint to see whether our thoughts have been on the right path. Thank you.